G'day viewers. In this segment I'll talk about how to set the retransmission timer. So this is a fun little topic. All we're trying to do is set that timer to decide when a segment is lost and when to retransmit. But it turns out that to do a good job of that we need to be able to adapt to the conditions on the network path. Here's the overall context for our topic. We're using a retransmission strategy as part of the sliding window. And the way in which we detect loss and hence decide to retransmit is by using a timeout. So we simply set a timer when a segment is first sent. And if an acknowledgement comes back, this is the normal case, then everything's good and we can cancel that timer. However, if the timer goes off, it means no acknowledgement has been received. We decide that the segment most likely has been lost and we retransmit it. So that's all the timer is used for. The difficulty that we're going to talk about in this lecture is how to set the value of that timeout. It turns out that it's important to set it to an appropriate level. If it's too short, if it's too long case first, then we'll end up wasting the network capacity. Because by the time the timeout is gone, our network path may have been idle for a long time when we could have usefully sent information. On the other hand, if it's too short, we'll decide to retransmit early when actually the packet had got there, it's just that the acknowledgement was coming from the other side. So these early retransmissions add load to the network when maybe the round trip time had already gotten high, and they're also somewhat inefficient. So we'd like to avoid both of these cases. So how do we find this value that's just right? Now, it turns out that it's fairly easy to pick a value on a LAN. That's because the round trip time is usually fairly short. It's also fairly fixed and predictable. In the internet at large, however, it's much harder to pick a reasonable retransmission timeout. And that's because the RTTs can be much larger. And they're also, it depends, they can also be short. And it's also the case that the RTT is much more variable over time. Both of these factors make it difficult to pick an appropriate retransmission timeout without erring on the side of being far too short or far too long. Well, let's look at a little bit of data to see that issue. Here's some data I took by using the ping program to send packets along the path from Barcelona to Seattle and back to Barcelona. And you can see on the y-axis here we have the round trip time in milliseconds. And on the x-axis there, we just have time in seconds. Wow, this data goes up and down. It's a little surprising, isn't it, to see? So actually there's a lower bound somewhere around here. This would be essentially the propagation delay. Plus maybe the time to transmit a packet, but if that's small compared to the propagation delay, this is mostly the propagation delay. So this is the minimum time that it could possibly take to send a packet along that path and get an ACK back. I keep saying packet, but here I'm really talking about segments because we're in the transport layer. Nonetheless, a message on the internet. There's also a lot of variation. Sometimes the round trip time from sending a packet and getting the ACK back is short. It's near the minimum, but at other times it shoots up, and you can see it bounces around quite a lot. This variation comes from many possible sources, but most likely from queuing. When packets get queued inside routers and they compete with other traffic from different flows, and it takes them a while to cross the network. So the round trip time really does jump around. For here it's moving from around 200 milliseconds to almost 900 milliseconds. So that's a substantial variation. Let me clean that up there. And this is the original data. So now we would like to pick those timeout values. What should they be? Well, here are just some fixed values I could pick. If we pick something down on the low side here that covers much of the data and is not much higher than the propagation delay, you can see that it still loses out a lot of the time. All of this area here, we would be deciding that packets were lost and retransmitting them even though they'd gotten through. It's just the delay in the network was higher. This probably means that the network is busy, so this is not really a very good time to be sending a lot of extra traffic. So we could use a higher timeout. On the other hand, if we set our timeout to the maximum we see over a period of time here, we're really, if a packet is lost due to some reason, corruption, we're really spending a lot of time in here and here, unnecessary time, to decide that something's happened to that packet. So neither of these are good. What we would like to do is adapt our choice of timeout to the actual network conditions. So over time, we would like to move from low to high, back to low again. That's what we want to do. How are we going to do that? Well, I'm glad you asked. We're going to use an adaptive timeout. Now the math looks a little hairy here. Don't worry, actually, it's fairly simple when you get used to it. For this adaptive timeout, we will simply keep smoothed estimates of the round trip time. So that's going to be like a moving average, just to keep its average value. And we'll also keep an estimate of the variance in the round trip time, because not only is its absolute level changing, but also how variable it is can change over time. So we update these estimates with a moving average. Let's look at this first one here for SRTT, that's the smooth round trip time. This equation says that the way we update the smooth round trip time estimator over time is we take 90% of its former value, that's the 0.9 times, and we feed in 10% of a new sample. That new sample is just the latest round trip time measurement we have. And this has the effect of, this is like a low pass filter, it's really averaging it and throwing away a lot of the ups and downs. We'll also run a similar estimator for the variation, and for this we simply keep 90% of our estimate for the variation from the last time, that's this factor, and then we fold in 10% of a new sample. And the new sample can just be the difference between the round trip time we just got and the smooth round trip time, because that's some estimate of how much it's jumping up and down. This is technically the deviation. Once we have these estimators, they sort of tell us roughly what's going on with the round trip time. And we can then set a timeout to be some multiple or combination of these estimates. The idea here is to come up with something which gives us a good prediction of the highest round trip time we're likely to see in practice right about now. The estimate that TCP uses, in fact, is the smooth round trip time plus 4 times the variance. It's unlikely to vary the round trip time by more than about that. Well, let's see how this works. Okay, so the blue curve here is our data, and I've overlaid 2 other computations based on the data on there. This line, this higher line here is the smooth round trip time. And you can see that it tracks the blue line just without all of the extrema there, so it's the smoother line in the middle. This line down the bottom, S-var, is tracking the variance in the round trip time over time. And you can see the variance is sometimes fairly low at the end here, but sometimes the variance jumps up and it's quite high, and this is when the signal is going up and down. So our estimator for the timeout is going to be the smooth round trip time plus 4 times the variance. And we hope that that will somehow be something like this. Let's see. Well, here it is. Well, you can see actually it did even a little better than my line. Here's the timeout, so the smooth round trip time plus 4 times the variance. And you can see that on the whole, this stays above the blue curve, but it comes down and it lowers itself so that at times when the blue curve jumps up, it's really not that much higher than the blue curve, so it's fairly tight. Yet it is shooting up fairly rapidly at a time when the round trip times seem to be climbing. Now it looks like just very occasionally our predictor could actually be a little low. If that's the case, we would end up doing an early timeout. However, that's pretty rare. Okay, so just to sum up, these adaptive timeouts are pretty cool actually. They're fairly simple to compute and they do a good job of estimating a reasonable timeout value based on the real round trip time. So they track it. You could see in the previous slide that the estimator went up and down as appropriate. It has little headroom, so it's usually not much higher than it needs to be, so we'll detect losses fast. Yet it also makes errors rarely, so it's not usually lower than the actual round trip time. So we should expect to have very few early timeouts. And even though we don't know it yet for sure, I can tell you that it turns out to be important to have good robustness and performance to have a good round trip time estimator in practice. Okay,